So you have example which is shown on your screen. This example we will use both horizontal separator as well as we will use uh, vertical separator. This will be a little bit different than normal, but you already have the idea of how to simulate, how to add the hypothetical component, right? So basically, they are using hypothetical component. You need to you need to add hypothetical component in this simulation in order to run the simulation. Okay, before I will jump again into the before I jump again into the example, again I want to repeat, okay, those who just joined, you have mid-exam 1 for chemical process simulation, which will be on 27th of October next week, okay? So just to again remind you that you have exam on 27th of October, which is Tuesday next week. What is included? Everything is included, including what you are getting today. Okay, even today is also. And also, again, a reminder for those who did not submit the assignments on Google Drive link that I shared class in the classroom. Please submit your assignments. Okay, this is very important. I still 11 students he did not submit the assignment, which is not good. Right. So let's go back again to the example. So we have an example which is shown on your screen. We have a feed stream. I will call that feed stream name oil sea line. Okay, the name of the feed stream is called oil sea line. The temperature, pressure, and the flow rate of this particular stream is 27.06 degrees Celsius, 1300 kilopascal, and 2511 kilomole per hour. Okay, these are the three things that we know about this stream. Obviously, we also know the fourth thing, which is the composition. Okay, so this feed is to be separated using a three-phase horizontal separator, and some of the information regarding the three-phase horizontal separator is mentioned here. Pressure drop, which is 100. The vapor outlet is, there are two pressure drops, okay, in this case. The inlet pressure drop is 100, and then we have the vapor outlet pressure drop, uh, which is leaving actually is 1100. Okay, this is the information that is required for three-phase separator. Some of the other things regarding this three-phase separator, it is a horizontal separator. The length of the horizontal separator is 9.6 meter. The diameter of this separator is 3.2 meter. Okay, so these are the information that you need to mention in the separator ratings. Okay, in the ratings. Okay, so after this, the oil produced need to be separated in whatever the oil that you're getting from three-phase separator. Obviously, in three-phase separator, you are separating the gas, you're separating oil, and also you're separating water. Okay, the oil that you're getting from this separator is to be heated and separated in two-phase separator. Two-phase separator is your vertical separator. Okay, so you need to separate this oil. After heating the oil, you need to separate them in two-phase separator. The oil is heated in a heater with a vapor fraction. This is the information that you need in order to converge the heater. Okay, the vapor fraction that is leaving the heater is 0.5, the vapor fraction. You need to neglect the pressure drop across the heater, and after that is the only thing you need. Okay, you need to neglect the pressure drop. It means whatever the pressure that is entering in the heater, same pressure is leaving the heater. Okay, similarly the temperature also, the temperature you need to mention also. Okay, so the pressure is 1200 kilopascal, keeping the same pressure. That is the pressure that is entering the heater. Okay, same pressure you will put it at the outlet also. Before the separation, the pressure drop is 400 Okay, after this one, after you will get your what you called okay, from here what you have, the pressure drop, the pressure is 1200 kilopascal, keeping the same pressure. Before the suppression, the pressure is okay. You need to use the same pressure, which is you can use it in the heater. Okay, when it is leaving from the heater, the pressure is 1200 kilopascal. This pressure has to be decreased to 400 kilopascal, okay, using a valve. After this, you will do this suppression, two-phase suppression. Okay, so I will do it one by one. Then you understand what I try to mean by this one. Okay, right. So let's start the simulation. Again, you need to open up Aspen Hysys and you need to start simulating. So I will keep this one on this side. I will keep this one on this side. Okay, regarding the composition, the information that is not shown here, I will put it in a separate Word file, which is probably you don't see it clearly. Let me increase the font. Right, I hope you can see this one now. So this is the composition that we have, and we have the composition for so up to here you understand what are the components. Okay, what is KC6, KC7, KC8, KC9, KC10, KC11, and C12? KC6 to KC11 are your hypothetical component. And as you know before, in order to create the hypothetical component, what we did previously, we use only boiling point, right? But I told you in the previous example also, the more information you have for the hypothetical component, the more accurate is your hypothetical component. Okay, so in this case, I give you a chart which contains more information. Uh, Not only they contain the information for boiling point, they also have molecular weight, liquid density, the weight, VC, which is critical properties also for all these components. Okay, these are the information that you need for from KC6 to C12 plus. Okay, so we have 1, 2, 3, 4, 5, 6, 7 hypothetical components. Okay, so this is the composition that is given to you. This is the information that is given to you. Using this information, you need to add these components. A little bit lengthy process, but obviously this is the real process that you will do in the industry. Okay, before I start, I want to add the components. So I will open my Word file. I will put it here so that I know which components I'm adding. Okay, so the first thing I need to do, I need to add the components. So I will put this one here so that you have an idea what I'm doing. Okay. So the first component is nitrogen, according to your Word file that I give you. H2S, second component. Third component is CO2, carbon dioxide. Then we have the fourth component, water. Now we have from ethane up to N-pentane. So I will just do it in just one click. I will add all these components in one click. So from ethane to N-pentane, select the first one, press shift and keep pressing and press the uh, last one. Okay, up to N-pentane. Add this one. Then I need to add KC6, KC7, KC8, KC9, KC10, KC11. Okay, so for that, what I need to do, I will click on the pure component box. I will change that one into hypothetical component, and from here I can go and create and edit hypo, the first one. Okay, after that I need to create a new hypo. Click on the new hypo. This is all you already done in previous chapters, I think. Okay, first one I can call this one KC, not double click, just click here and call this one KC6. Now I will go and see what are the properties that is given for KC6. So I have the boiling point for KC6, which is 63.9. I have the molecular weight for KC6, which is 84. Pay attention, and this one is just you need to key in the information. The liquid density is kg per meter cube is 689.9997 kg per meter cube. The critical temperature, which is in degrees Celsius, is 234.65. The critical pressure is in terms of bar G, bar gauge. Obviously here it is mentioned in terms of kilopascals. So instead of going back and change it from there, I will just use the information and I will use the unit converter. Okay, 32.82, and this is in terms of bar G. So I will use the bar G option. Okay, if you go down, you will see bar G here. Okay, just select bar G. So it will convert the unit into bar G and then put it here. The critical volume in meter cube per kg mole is 0.35, and the eccentricity, which is mentioned in terms of W here, which is basically show you the shape of the molecules, is 0.271. So this is the information we have for KC6. Similarly, I will do it for others. So I will call this one KC7. Then similarly, the boiling point is 91.9. Molecular weight is 96. Can you see my screen easily? There's no problem. Can you read what is happening?
Yes, Doctor.
Yes, doctor.
Yes.
That's good. Then the liquid density is 727 kg per meter cube. Critical temperature is 269.05. Critical pressure, make sure it is in bar G. Here it is mentioned kilopascal. You can do some mistakes here, so make sure you don't do mistakes in unit conversion. So convert this one into bar G. Okay. Then critical volume will be 0.38. So then you have eccentricity, which is 0.31. So already added KC1, KC6, and KC7. Now we will add KC8. This is the situation you normally face in the industry when you have the components, but you don't know the information of the component, but you have the information regarding the properties of the component. Okay, so in that case, you need to use how to use the properties. This is how you can use it. Molecular weight is 107. Liquid density is 749. Critical temperature is 297.45. Just wait. Okay. The critical pressure is 29.51. 29.51 bar G, which is this one. And critical volume is 0.431. And eccentricity is 0.349. There is no shortcut for adding all these components. Okay, you have to add them manually by one by one. Then KC9. KC9 is the boiling point for KC9 is 142.2. Molecular weight is 121. Liquid density is 768. Critical temperature is 325.15. Critical pressure is 27.37 G, which is gauge pressure in terms of bar. The critical volume is 0.431. and lastly the centricity is 0.392. Okay, another one, KC10. Then the boiling point for KC10 is 165.8. Molecular weight is 134. Liquid density is 782. Critical temperature 349.05. Critical pressure is 25.3 in terms of G again. Okay, and then we have the critical volume 0.537. The eccentricity is 0.437. In another one, that is KC11. KC11, we have normal boiling point is 187.2. Molecular weight is 147. Liquid density is 793. Critical temperature is 370.15. Critical pressure is 23.51 RG. So just go down, select RG. Okay. Critical volume is 0.587 and eccentricity is 0.479. And the last one, which we can call it C12 plus. That one have the boiling point is 463.15 degrees Celsius. Molecular weight is 408. This is a heavy component because it is have very high molecular weight. Liquid density is 921. Temperature is 627.31 Celsius. Pressure is 9.95. Again, bar G. Okay, you can have the option to change these properties in units before. If you do that one, obviously it will be a little bit faster as compared to this one because I need to change this one manually. Critical volume will be 1.6455. Eccentricity is 0.9071. Okay, so when you add all these components, select all of them by clicking first one and shift and select the last one, and then you can just add all. So all of them will be added here. So you can see here, if you add correctly, you can add all these components on the list. Okay. Now we need to go to fruit package. We need to select a fruit package, and the name of the fruit package that we are selecting here is called Ping Robinson. Now after you do all these steps, you go to simulation environment. And in the simulation environment, the first thing you need to do is to add a material stream. Okay, I can go inside of the material stream and I can call this material stream oil C line. Okay, so this is the oil C line material stream which contain light. The idea of adding the hypothetical component and C12 plus fractions and the light components, it means like we are creating one stream which contain light components, which contain middle components, and which contain heavy components. Okay, so that is the idea of doing all these previous steps. Okay, now the temperature for this stream is 27.06, and let me change this. No need to change even its setting. It's mentioned 1300 kilopascal here, so I just keep it at 1300 kilopascal here pressure. the molar flow rate we have is 2511 kg mole per hour. Okay, and again we need to key in all the composition, so I need to use word file. Okay, so this will be in terms of mole fraction, so I will choose I think I can copy all of them and I can put it in just one click. I think I can do this. Try. Yes. Okay, so if you type in the word file, you can copy all this composition and you can paste it here. Fine. Then you, if it is coming above 1, then you need to normalize it, make it 1. Okay, and then press OK. So if you do it correctly, then your stream will be converged and you can have option, which you can see this one here. Okay, now according to our question, we need to separate that into a three-phase separator. So I will use the three-phase separator which is mentioned here, and I will put it here. Okay, I will zoom out a little bit so that you can clearly see it. Okay, again, wait. Okay, so inlet stream will be your oil sea line, and your vapor stream will be your gas stream. This is your oil, and the last one is your water stream. Okay? So that is the only thing required. However, since I have some information regarding this, extra information regarding the separator, so I have to key in those information also. Okay. First, I need to key in what is the inlet pressure drop. There are two pressure drops that we have. Okay, inlet and vapor outlet. So for inlet, we have the pressure drop which is mentioned in kilopascal is 100 kilopascal. For vapor, I have 1100 kilopascal pressure drop that I need to mention here. Okay, remember, you need to go to parameters and you need to mention these two pressure drops here. Secondly, I need to have some information regarding the size and the length and the diameter, and that is the information that I can key in by using rating. So we need to go to rating option, and if you look at here, we have the orientation which is horizontal. Okay, that is fine. However, the length is meant, you can have either you can either put the volume, you can even have the option to put diameter, you can have the option to put the length, and you have the option to put the height also. Okay, however we only have the length and the diameter. So the length I have is 9.6 meter, and the diameter I have is 3.2 meter. Okay, so this is important, right? So this is the information that we have for this particular separator. Okay, so based on the separator is already converged, but we need to put those information to see that how much is the size to let the Hysys know the height, the length, and the diameter of the separator. After this, you go to the next page of the slide, and now here I need to close this box. So if you done it correctly, you will have a simulation like this. Okay. Now, what we will do? So we are getting gas on the top, we are getting oil on the middle, and we are getting water on the bottom. This oil might contain some light components which I want to separate out. Okay, but this oil has a temperature which I want to increase. If you look at the temperature here, uh, you can use the heater to increase the temperature of the oil. Then you will decrease the temperature of the oil. Then basically, when you increase the temperature of the oil, then you will use the separator, the vertical separator for separation. Okay, so we need to install a heater. So if you install a heater, you can put it here. Double click and open the heater. Now the inlet, we already know we have the inlet which is oil. Okay, I can call this one heated. The outlet information I don't have, so I can call this one heated oil. Okay, or just heated also is okay. Since it is a heater, we need energy stream also for the heater. Okay. So when you provide all this information, then it is asking you what is the delta P. And since we know that we don't have any pressure drop here, or we have zero pressure drop, so we go to a parameter and we put zero pressure drop. Okay. Now, since the heater require one information for the outlet stream, which is the temperature, uh, temperature or pressure. So if you look at your question, the question is saying that you have the information only in terms of vapor fraction. If you go to your worksheet, you have the inlet to the heater, the outlet of the heater, and then you have the energy stream information. So if you look at here, only two things are basically blue. Since we know that there's a no pressure drop across the column, so whatever the pressure that is entering, the same pressure will be leaving. So this is the information we already have. We don't have, we must have the temperature, or we must have the vapor fraction. In this case, we only have the information for the vapor phase. In order to run this simulation, in order to make the degree of freedom 0, we need to provide at least one information here at the outlet. So since we only have the vapor fraction, which is 0.5, I mentioned I will put 0.5. When you press enter, you can see here, using this information, using the same information, they will calculate the temperature for us, which is 307. So the heater is increasing the temperature from 26.95 to 307 degrees Celsius. How they calculate? What we give them, that we want two phases at the outlet. What we want from this simulation, that you take the oil inlet and you create two phases of this oil. So at what temperature do you want to create two phases of the oil? So I can say here that please create two phases 50-50%. 50% gas phase or 50% liquid phase. That's the reason what I put it here. So they will create two phases, but they also check at what temperature you can get two phases. So they indirectly calculate the temperature for us, which is 307 degrees Celsius. So at this particular temperature, they will create two phases. Okay, that is the reason why we install heater. Yes. Any question?
No, thank you, doctor.
Okay. Then after you do this, then you close it. You can see you have the simulation like this. Okay. So now we know that we have two phases here. We can use a vertical separator or two-phase separator to separate those two phases. Okay, because here the phases are mixed, is not separated. So we need to install a separator to separate these two phases. So the reason why I'm installing a heater to create two phases, so that I can use separator, two-phase separator to separate them. Okay. Now before I install that one, I need to go and see what the question is saying. Before the separation, so before I will use the separation process, I need to decrease the pressure of the stream to 400 kilopascal, because if you look at the pressure is 1200 kilopascal. This is very high pressure. Okay, this, and at this particular pressure, you might not get a proper separation in the separator. So what you need to do, you need to decrease the pressure of the stream. So how you can decrease the pressure of the stream? By using a valve. Okay, so you select the valve and put it here. Then double click and open the valve. And the inlet to the valve will be your heated stream, which you mention here as heated. The outlet of this one is to be, I will call this one to be separated. Okay, you can call it any other name also. There's no problem. And the pressure drop, I will keep it as 400 kilopascal. You can see here the pressure drop is 400 kilopascal. Either you can give information like this in pressure drop, or you can go here also outlet and you can give the information here. So since it is better for me to put the information in the pressure drop part of the valve, so I can call the pressure drop has to be 400 kilopascal. So 400 kilopascal pressure is dropping. So what is the pressure here before? 1200. So 1200 minus 400, the pressure will be 800. That is the pressure that is going out from the stream. Okay, that is not the pressure of the outlet stream. This is the pressure dropping across this valve. Okay, I think before I said this is the pressure that is leaving, but this is not the pressure that is leaving. That is the pressure drop across the valve. Okay, so technically the pressure outside will be 800 because the pressure is here is 1200. Pressure is dropping 400, so 800 minus 1200 is 800. So 800 is the pressure. You can see on your screen the information that is mentioned. Okay, then we are in a situation, or we are clearly in a situation that we can use the separator to separate our phases. So again, you open the vertical separator. You can the inlet. This will be to be separated. The outlet, I can call this one vapor. Okay, before I add the liquid steam, just to remind you, whenever you are using some names in the simulation, please make sure don't use the same name again. Okay, uh, change with one or two, change the names. Don't use the same name. For example, here I write to be separated. I cannot write to be separated here because if I write this will connect this to this one. Okay, so make sure different names you will use. Whenever you add different process, you will use different. Don't use the same. Right. For liquid, we can call it liquid. Okay. So after you do this, then it will be converge. Now you can go and check the composition of your vapor phase and the liquid phase. In order to check the composition, you go and you can check either you have the information here, you have some vapors here, or you don't have any vapors. If you go to composition, obviously, if you look at here, you can see we have some light components. So if you look at here, this is your mole fraction composition. Okay, so you have nitrogen, you have carbon dioxide, you have small amount of water, you have methane, ethane, propane, and this is how the composition is being distributed in vapor phase. If you look at your liquid phase, let me click this one and then go to worksheet and composition. Now I can compare. Okay, so this is what is entering. Okay, and this is what is being separated. So in the liquid phase, you can see here we have 77% is C12 plus fraction. Means like heavy fractions. You can clearly see from here that you have removed 77% of the heavy fractions in the liquid phase, which is good, right? Obviously, this is still still you have the remaining amount, which is not go here. You can improve this separation. Okay, again, you can improve this separation if you use a distillation column. Obviously, in this case, we only use a separator, and you know that the separator don't have trays inside. Okay, if you don't have any trays inside, then there's less mass and heat transfer. If you have a less mass and heat transfer, then the separation is weak. Okay, still they able to separate 77% of C12 fraction in the liquid phase. And you can see here from this chart also, you can have a majority of the gases that is removed on the vapor phase. Okay, so majority of liquid is removed in the liquid phase, and majority of gases you get on the vapor phase. So this is the idea. You have the idea behind this simulation, that you have a stream of oil, gas, and some water. You create that stream. Okay, obviously in the industry, if you're working, they will take the oil from the ground and they need to check that one, right? But in this case, just we want to create one stream and we want to see if we have gas, if we have oil, and if we have water in that stream, if we can use two different separators, can we able to separate the liquid out from the vapor? So technically, yes, you are getting 77% of the heavy fractions on the bottom, and the majority also you're getting whatever is left, you're getting on a vapor. So if you look at this whole thing, what do you think that in your stream that is your feed, which fraction is the most that you have? Any idea? So in your inlet stream, What do you think? Either you have majority of light components, majority of heavy components. What do you think? Any answer? Looking at your feed stream, what do you think? And looking at your suppression, okay, what do you think that in your feed stream, which components are more, heavy components or light components?
Heavy components.
Oh, okay. Yes, that is the reason why you can see here you are getting 77% of the liquid and very small amount, which is like, let's say you can have 20% or 25% of vapors. But this kind of a stream is basically a stream of the oil which we are getting from the. You normally, if you're working in the petroleum, what you call petroleum sites, you have two different types of sites. One type of site you have purely gases, majority is gases, right, coming from the ground, and some of the fields that you have, some of the wells that you have, they have only oil, and some of the wells that you have contains both oil and gas. And some of the wells you have 70% of wells, 70% of oil and 20% or 30% of gases. So this is the example of those wells which contains 70% or almost 70% of the oil. The remaining will be gas. Okay, so this is how you can check your stream also. But obviously, this is the simulation. Okay, in real environment or if you're working in the industry, what you normally do, you take the oil from the ground, from the wells, and then you do experimental tests, okay, in order to check that how much of the light components you have, how much of the heavy components you have. So based on your results, you need to install an industry that is purely working on the basis of what type of feed you have. For example, if your feed contains more oil, okay, then your industry is based on removing purely oil, okay, and less will be gas. But in case if your feed stream contain more gases, so your whole industry is based on removing the gases, okay, or basically purifying the gases. So that is very important before you install any industry. Okay, you need to first check what is the composition of your feed. Okay, this is primarily tests like you do this test before you set up your industry or you want to spend money on setting up an industry. Okay, so this is the idea uh, of doing all this simulation. All right, now this is the end of separator example. I want to add another example, not example, but I want to add a vector. Okay, find out. So suppressions, I think we can cover enough information for suppression. So I think it's easy for you now to understand if you have to simulate the separators. Doesn't matter if it is vertical or horizontal. You can choose separator. Okay, one more thing I want to add here. All of these simulations are steady state simulations. Okay, you can convert them into a dynamic simulation also, but because we don't have the course is the limitation of the course is only on steady state conditions. Okay, so that is the reason why I'm only uh, teaching you steady state. Okay, maybe in future if the course contents are changed, then we can add dynamic simulation also. Okay, so let's go to lecture notes, and I want to add a rector now. Okay, so I will share this one later on. Okay, so you can go through with this lecture note. Okay, so conversion reactions on many as if you know the theory part of this course that we have covered so far. What we studied it in theory part is that the reactors are playing a key role in any industry, and it is the heart of any industry. Mostly the conversion after the conversion reactions, then we will do separation, and then we do further things, recycle and everything. But the first thing we need to do, if you look at if you have seen that onion model, onion, in the onion model, the middle part is conversion reaction, right? Means like the reactions. Then after the reaction, we will do separation. Then after this one, we will do many other things. But the key part is is the reactions. And if you look at chemical engineering point of view, there are many types of reactions. Okay, you have synthesis reaction, you have conversion reactions, you have equilibrium reactions. Okay, so many different types of reaction that is happening in the chemical industry. In this course, or we will talk about few of the chemical reactions. Okay, the first one I'm trying to start here is conversion reaction. So in conversion reaction, as you should know that we have the feed, and that feed has to be converted into the feed contains reactants, and that reactant has to be converted into products. So how they convert? They will convert. They will lose what you call is property, and they convert them into a product. So the reactant will lose, and then it is converted into product. So this reaction type does not require any thermodynamic knowledge. Okay, so particularly this kind of a conversion reaction, you don't need any thermodynamic model knowledge. You must input stoichiometry. Stoichiometry means how many moles of A is entering, how many moles of B is entering, and how many moles of C that you are producing, and how many moles of D you are producing. Okay, so basically you need to understand what is the stoichiometry that is happening. You need to know that the first thing that you need to know that you have a chemical reaction. The second thing you must know that the chemical reaction has to be balanced. Okay, if the chemical reaction is not balanced, you cannot use Aspen Hysys. It must be balanced. And the third thing you need to know is the conversion. How much conversion of the base reaction and which reactant is reacting more? Okay, how much that reactant is converting, the conversion. So how much percentage of conversion is happening? That is the information you need to provide. Okay, you need to have a proper stoichiometry, like the chemical reaction is there. It must be balanced chemical reaction, and you must have the information of the conversion of the reactants. Okay, how much percentage of conversion you have. The specified conversion cannot be exceed 100%. So make sure it has to be total 100%. You need to put less than 100%. Obviously, there's nothing can be reaction cannot be 100%. Okay, maybe it is 90%, 70%, 85%, but cannot be 100%. The reaction will proceed until the specified conversion has been reached or the limiting reactant has been exhausted. Means that the reaction will only able to complete when you know that reaction is complete, whenever the specific conversion that you put has been reached, or the limiting reactant which will be reduced first will be totally removed, or totally will be exhausted. That is the only way we understand that reaction has to be completed. Okay, conversion reactions may not be grouped with any other form of the reaction in the reaction set. We'll talk about this one later when we have other sets. Okay, you have different types of reactions. You have conversion reactions, you have synthesis reactions, you have equilibrium reactions. So every set or every group, okay, is created inside Aspen Hysys. Only inside that group you will put one type of reaction. For example, if you have 3 or 4 or 5 reactions, and all of those reactions are conversion reactions, these all reactions will go into one group. Okay, similarly, if you have one reaction which is conversion reaction, other reaction which is equilibrium reaction, then conversion reaction will go to one group, and equilibrium reaction will go to another group. Okay, you will create another group for different conversions. That is called reaction set. That group is called reaction set. I will talk about this one when we start simulating. However, they may be grouped with other conversion reactions and ranked to operate either sequentially or simultaneously. So if you have more than 2 reactions, you can mention inside Aspen Hysys which one is ranked more, or which one is happening more as compared to other. Okay, for example, if you have 2 reactions, one reaction is happening 70%, other reaction is happening 30%. So you can say reaction number 1 is ranked higher than reaction number 2. Okay, so how you can rank them? You can rank them by putting the value 0 or 1. If you put 1, it means it is the higher rank. If you put 0, that means it is lower rank. You don't understand these things right now, but when you start, then you understand. Okay, but ranking is very important. If you have multiple reactions, you need to tell Aspen Hysys which reaction is happening more, which reaction is happening less. So the way you can tell Aspen Hysys the reaction is happening more or less If you put 0, it means the Aspen Hysys is considering that direction is happening less. Or if you put 1, then Aspen Hysys will know that direction is happening more. Okay, this direction is happening more as compared to second direction. Just as with a single direction, simultaneous directions cannot total over 100% conversion. So if you have more than one directions, then the total conversion cannot be exceeding more than 100% of the same basis. Conversion reactions cannot be used with plug flow reactor. Okay, this is another thing. If you're using plug flow reactor or CSTR reactors, you cannot use conversion reactions or conversion reaction set in that case. Okay, so make sure whenever you are using conversion reaction set, you must have a conversion reactor inside the Aspen Hysys. If you're using a conversion reaction set, but inside Aspen Hysys you are using plug flow reactor or CSTR reactor, it will not work. Okay, so you need to use a proper reactor that is called conversion reactor. Okay, so again, the learning outcome of this exercise will be you are able to simulate conversion reactor in Aspen Hysys, and also you are able to add reaction and reaction sets. This is something that you are learning extra here. Okay, normally what you do in previous cases, you are selecting the components, you are selecting the fluid package, then you will jump straight to simulation environment. However, in this case, we will not only add components, we add the fluid package, but we will also add the reaction set, okay, or the reactions. And once you add the reactions, then you need to add this reaction to the fluid package. For example, if you're using King-Robinson equation of state, this reaction set has to be attached to this fluid package. There's an option here in Aspen Hysys that will show you how you can attach the reaction set to the fluid package. After you do all these 3 steps, then you can go to a simulation environment and start simulating. Okay, let me talk about the problem statement what you have. Let me zoom in so that you understand first what is the problem statement, and then we will proceed. So the interest in the production of hydrogen from hydrocarbon has grown significantly in the last decade. This means like this statement says that the hydrocarbons, you know that hydrocarbons contain hydrogen part and they also contain carbon part. Okay, so these days producing hydrogen from hydrocarbon, because you know that hydrocarbons contain both hydrogen and carbon, you can remove hydrogen from hydrocarbon and use it later on. If you remove hydrogen purely from hydrocarbons, and you know that hydrogen is a clean burning fuel. Okay, why we are saying that hydrocarbons are not clean burning fuel? Because they contain carbon. That is the reason why it is not clean burning fuel. But if somehow you are able to extract the hydro part from the carbon part, you can remove the hydro part, and that hydro part is called hydrogen, which can be used as a fuel. And this is a clean burning fuel because this does not contain carbon. Okay, and this is very much popular. You can get hydrogen from water. You know that water contains 2 hydrogen. You can get hydrogen from hydrocarbons. Okay, so both steps you can use. You can take out the hydrogen from hydrocarbons or water and then utilize it later on. So now the question is that this will show you the information that why it is important. Now, efficient production of hydrogen is enabling technology. This means like this is a new technology or new popular technology directly related to the fuel cell energy conversion devices. So the hydrogen that you're producing, you can produce hydrogen and you can put them in a fuel cell, which can be used as an energy fuel cell. Fuel cells are just like a normal cells, not like a normal cells, but they inside those cells they are using hydrogen. Okay, they are special kind of cells which are using hydrogen. So how the fuel cells are working? Inside the fuel cells we have both cathode and anode. Okay, those cathodes and anodes are very sensitive to carbon dioxide or carbon monoxide. Okay, so when you are producing what you call inside fuel cell, when you are producing hydrogen, you should put hydrocarbon inside the fuel cell, and if you start producing or if you have hydrogen in the fuel cell, and if that hydrogen is not pure hydrogen, it contains some carbon also, it will cause problem to to the cathode and anode. Okay, so when they cause problem to the cathode and anode, then you will have problem inside the fuel cell. Okay, or you cannot uh, utilize, or you cannot store that energy inside the fuel cell efficiently. So what is the idea? We have we need to remove as much as carbon from this from hydrogen, so that a hydrogen is pure from carbon. Okay, keeping this thing in your mind, now the question starts. Okay, the conversion of the fuel in this case is methane. The conversion of fuel to hydrogen can be carried out by partial oxidation. So how you can produce hydrogen from fuel oil? By partially oxidizing this hydrocarbon, which is methane, or fuel, which is methane. If you partially oxidize it, you will get carbon monoxide and hydrogen. Okay, this is the first reaction, or the main reaction. The second reaction is that this leftover methane or hydrocarbon is again oxidized, and they'll produce carbon dioxide and hydrogen. So we have two reactions. One is partially oxidized and the other is oxidized. And in the products, we are producing carbon monoxide, hydrogen, and carbon dioxide. The problem in this kind of reaction, you need only hydrogen, but you're getting carbon monoxide, carbon dioxide, and hydrogen. So the idea is you can minimize this one, which we will do in the next chapter. First, we will see how much of carbon monoxide, carbon dioxide, and hydrogen we are producing. In the second part of this whole question, we will try to minimize carbon dioxide, carbon monoxide, in order to increase the production of hydrogen. Okay, that we will do later on. But first, in this question, we want to see how much of carbon dioxide, carbon monoxide, and hydrogen we are producing by partially oxidizing it, or then we are further oxidizing. So we need to develop a model that represents the partial oxidation of methane to produce hydrogen. Okay, this is our main task. And if you look at in the next chapter, we talk about what there's another process that is happening, which is happening in the next part of the this exercise. Okay, the first thing you need to know that you will use Ping-Robinson equation of state as your property package, and the components that you are using is methane, oxygen, nitrogen, carbon dioxide, carbon monoxide, carbon dioxide, and hydrogen. If you look at your components, you also have a nitrogen. What is the role of nitrogen in this reaction? There's no role, right? So why we are adding nitrogen? Any idea? Why we are adding a nitrogen in the components? They are not used inside the reactions. Yes, students sleeping.
Because it's inert gas.
Yes, that is the reason. It is inert gas. And similarly, how you can get oxygen? Obviously, you can
from
get.
the air and the air.
Yes, when you're getting oxygen from air, you're also getting nitrogen. You cannot get
Yes.
only pure oxygen, right? That is the reason why we are adding both oxygen and nitrogen. Okay, so let's go to the simulation environment and see how we will do this whole process. So let me go back here. The first thing I need to do is I need to open a new simulation, new case. If you open the new case, you need to add the components, and we need to add, not set this one. I need to delete first. We need to add the components. Add components, and here we need to add methane. We need to add, sorry, my Aspen Hysys stuck. Okay, I will restart Aspen Hysys. Happens sometime when you're clicking on these softwares, it may crash. Okay, so make sure you don't play with Aspen Hysys too much. Okay, just do it slowly. New simulation. Start again. So we add the components, and we'll add methane. Be very careful with the using Aspen Hysys, very sensitive. oxygen, then nitrogen, then carbon monoxide, which is the last one. Then we have carbon dioxide, and then we have hydrogen. Add all these. How many components we added? 6 components. So 6. Then the fluid package will be Ping-Robinson equation of state. Okay. Then you can, instead of going to simulation environment, we need to do a third step, and we need to create a reactions. For reaction, we need to click on the reaction tab. Look at here. After petroleum assay, you have a reactions tab. Okay. Click on the reaction tab. Again, you will see a window like this. Here you need to add reactions. So these two reactions that you mentioned here in the question, it must be helpful here. Okay. First, the reactions has to be completely balanced. Okay. In order to enter the information of the balanced chemical reaction is very important. Okay. And we must use these two reactions here. So we know which one is reactant and which one is product. And their sequence is very important. Means the methane is first, oxygen is second, third is carbon monoxide, and fourth is hydrogen. In the second reaction, again, methane is first, oxygen second, carbon dioxide third, and hydrogen fourth. This sequence is very important, and the balancing is also very important. If you look at here on the bottom, you have the option called add reactions. If you click on add reactions, you will get this small window. In this window, you have the option to add conversion reactions, and there are other types of reactions that you also have. Okay. However, we are only concerned with this particular case. We are concerned with the conversion reactions. Click on the conversion reaction, and then press add reactions. Nothing happens, but it happened behind. Okay. You close this box. You can see behind you, you have created a reaction, active reaction, that the name of this is RXN-1. Okay. You need to add the reactants by double clicking. So this is the thing that is by default created. So what you need to do, you double click and open this. Once you double click and open this one, you will see this window. Can you see the window on the screen? Yes?
Doctor.
Yeah.
Yes. Okay. So I want to see, please pay attention. This is very important. If you miss this one, then you miss many things. Okay. Look at your first reaction. The first reaction, first is methane, second oxygen, third carbon monoxide, and fourth hydrogen. So add the first methane, second oxygen, third carbon monoxide, and fourth hydrogen. Okay. You add the first reaction nicely. Now you need to add the stoichiometric coefficients. Means this one have 1, that was not mentioned. The stoichiometric coefficient of oxygen is half, 0.5. Stoichiometric coefficient of carbon monoxide is 1, and hydrogen is 2. However, how Aspen Hysys will know that which one is reactants and which one is product? Okay, so the one which is reacting, or which are the reactants, you need to mention them in minus. Okay, it means like Aspen Hysys, if you put -1 here, this is 1, right? But if you put it here, you put -1. So Aspen Hysys will know that methane is the reactant because you put -1, not 1. And here it is half, positive half, right? You need to put -half in oxygen. If you put -half in oxygen or -0.5 in oxygen, it means like Aspen Hysys will know that this is also a reactant. For the product, we just put 1 for carbon monoxide. So now Aspen Hysys will know that this is the product. Similarly, hydrogen, that is 2, we put +2 here. So Aspen Hysys will know that this is the product. Okay. So by keeping minus and positive sign, we'll know Aspen Hysys that which one is the reactant, which one is product. So the stoichiometric coefficient of methane is 1, which is not shown here, but it is 1. We can write -1. Okay. Similarly, the stoichiometric coefficient of oxygen is 0.5. We can write -0.5. Okay, because this will show that this is a reactants. Similarly, carbon monoxide is 1, so I can put positive 1. So because these are the product, so positive 1. Similarly, hydrogen 2, I will put positive 2 in order to see that this reaction is, and this is the reactant. Okay. Now, if you look at on this part of the window, you can see we have the base component. So if you look at your reaction, this is your reaction. In the reaction, in both the reaction, the base component is methane, which is converted, right? The thing which is converted is methane, which is the most important reactant. Okay, so the base component is the component that you must be shown here. Okay, if you look at here, we have two reactants. One is methane and oxygen. How they know methane and oxygen is the reactant? Because they are using this information. If you put -1 for methane and -0.5 oxygen, it will come here that these are the reactants. But in these two reactants, which are the main reactant that is converted? Methane. So methane has to be here. Okay, the main component. And you know that we have many reactions that is happening in liquid phase. We have reaction that is happening in gas phase. We have reaction that is happening in both phases. So I will say that this reaction is happening. I don't know exactly which phase they are reacting. So in order to be not to be confused, I will put overall. Okay, I don't know. Maybe they will change inside. The phases will change inside. So I will put overall. Okay. If you look at here, C naught, C1, and C2. Before looking at this one, you look at this formula. Okay, what this formula means, like the formula conversion percentage, which is equal to C naught plus C1 T is the temperature, plus C2 T square. This is the formula. In order to find out the conversion, you need to know what is the parameter C naught, what is the parameter C1, what is the temperature, what is the parameter C2, and the temperature. However, and temperature is in terms of Kelvin. Make sure it is in Kelvin. If you put all this information here, you can able to find out the conversion. Okay, but since we don't know exactly what is C1 and C2, the only thing we know is that this reaction is happening 40%. Okay, so if we know that this reaction is happening 40%, then what we need to do, we will ignore this part, and if I put 40 here, okay, replacing the C naught with 40, this means the conversion is 40%. Okay, in exams, if I give you the value of C naught, C1, and C2, and if you know the values of temperature also, you can use this whole formula to find out the conversion. Okay, and remember the temperature is in terms of Kelvin. You cannot use degree Celsius in this question. But if I give you the conversion directly, instead of I giving you the values, I say this reaction is happening 40%. Then in that case, indirectly, it means the C1T is ignored, C2T squared is also ignored. So these two things will be ignored. Now only thing is left is C naught, and that will be your percentage, which is like in this case, I can say this reaction is 40%, so I will put 40. This means this reaction is happening, this conversion is happening 40%. Okay, if you put all this information correctly, you can see the balance, your balance error. The reaction is balanced. How I know the balance is correct balance? The balance error is 0. If you have a proper 0 balance error, it means like your balancing is correct. It means like this information, the stoichiometric information that you're putting is correct. Okay, and you will get a green signal with option called ready. Okay, once you do this, then you can close this box. You add first reaction, but it is only first reaction you add. Okay, now you need to add a second reaction, which is this one. CH4 plus oxygen gives you carbon dioxide and hydrogen. So you can see the first is methane. Again, you need to click on add reaction. And in this section, because this section is also conversion reaction, you will pick up the conversion reaction. You add the reaction, nothing happened here, but it is happening behind. So again, now you double click and open. You can rename this one also, okay? You can also rename this one if you want. Either you can rename it here or you can rename it here also. But let's say I need to go to reaction number 2. And here, the first component is methane. Second component is oxygen. Okay, second is oxygen. Third is carbon dioxide. I will call carbon dioxide. And fourth is hydrogen. And the stoichiometry here is for methane -1, For oxygen, also -1. For carbon dioxide, +1. And for hydrogen, +2. If you do it correctly, you'll get zero balance error. Okay, this is how to show that your equations are completely balanced. Okay, for second reaction, the conversion that I have in the question is, I think 60%. Yeah. So this C naught is 60. Now you add the two equations. Now, since I told you before, uh, whenever you have a multiple or simultaneous reactions, ranking is very important. Ranking will show which reaction is happening more or which reaction is happening less. Okay. So how you will add this thing? You need to click on ranking option. So in the reaction, you can see here the rank is by default both have zero rank. Okay, but you know that the second reaction is conversion is more, so I can put 1 for the second reaction because second is happening 60% and the first reaction is happening 40%. So second have more conversion. So I will click on the second one. So the way Aspen Hysys know that which reaction is ranking more by using 0 or 1. 0 means the reaction is happening at low rank, and 1 means the reaction is happening at higher rank. Okay. Then after you put the information, you close this part, the ranking is done. Now you can see on your screen there's the option says that not attached to fluid package. FP means fluid package, which is in this case is Ping-Robinson equation of state. So you need to add these reactions to your fluid package, which is here. So how you can add the reaction? You click on add to fluid package, and here now it will show you that this is your fluid package you want to add. You said yes, I want to add this reaction to this fluid package. So click on add set to fluid package. Once you do this, now it is ready. Okay, now you can go to a simulation environment, and now you can do the same process. The first thing you need to do is to add a material stream. Okay, so we have two material streams that is entering. As I told you, according to your reaction, your methane is entering separately. If you look at your reaction, this is your reactants, right? Methane and oxygen. So methane is entering separately, oxygen is entering separately to the reactor. Okay, so we have two material stream. One is for the methane, other is for the air. Okay, why air? Because from air we are using oxygen. Okay, again, you double click and open the first one. I can call this one methane. Okay, this is called methane stream. The temperature of this stream is 25 degrees Celsius. Pressure is bar. I can change the unit set here, but I just want to use it. I want to use the unit converter here. So 2 bar means if you add 2 and change into bar, it will convert into kilopascal and put it here. So 2 bar means 200 kilopascal. The molar flow rate is 100. I put it here. And the composition, since it is purely methane, we don't have any other thing. We have only methane that is entering. So put 1 for methane only. Okay, because this stream contains only pure methane. So that is converged. Now click the second stream and call this stream air. Okay, and in this stream we need to add 25, again same temperature, pressure again same. So both temperature and pressure for both streams are same. Okay, the molar flow rate is different. Is in this case it is entering, so 260 means as compared to the methane we are adding more oxygen. Okay, so oxygen is in excess that we are adding. Then we can go to composition, and here if somebody is asking you what is the composition you need to add, you know the composition of air, right? Air contains 79% nitrogen and 21% oxygen. So we'll put 21 for oxygen and 79 for nitrogen. Okay, don't ask me this question, doctor. You don't know don't give us the composition for air stream. You already know from indirect. Okay, indirectly. Okay, when you done this one, you already created the two streams. Now you can add a conversion reactor. Okay, maybe if you are using the old version, you don't have these tabs. Okay, you can search the reactor inside. I have the option to enter the tags, the tab. In the tab, I have many reactors. Okay, This one is CSTR. This one is plug flow. This one is called conversion reaction. Make sure you use the right reactor. So in this reaction, if you see A and B inside, that is the reactor that you need to choose. So that one, click here and put it here. Okay. And the other thing which show you which reactor is correct, you can see in the middle it says C. C means conversion. Okay. If you choose the right reactor, it is shown here also. And also you can see here, if you just don't click here, just scroll your mouse on the top, you can see the name appears, conversion reactor. Now what you do, you double click and open this reactor. Again, you need to now here it is very important that the inlet stream has to be in sequence wise. You know that your first component or first reactants are methane. Okay, so the first reactant is methane, so you add first methane. Okay, if you click here, it will show you alphabetically, but the first has to be methane, second has to be air. According to your reaction, the methane is your first reactant and air is your second reactant. After you add this one, you need to click here and add vapor. I could call this one vapor, and I can call this one liquid. Okay, now everything is done, but where is the reaction? I need to add a reaction also, right? So you need to click on the reaction tab here, and in this small window here, if you click here, you can see the set that you already created before. The group that you created before is called set-1. Click this one, all of your reaction will appear, okay, and it will show up here. So this will be converged, it will be okay sign. If you look at here, it is already converged. Okay, now if you want to see what is the composition of your vapor stream and composition of your liquid stream, again you can do with a table. You can show table here, okay, and then you can go one by one, and then you can add the composition. Okay, just double click and open this one, remove the variables that is not required. What you need to know is how much is the flow rate for the vapor stream and how much is the flow rate for the liquid stream. So you click on master component. You click on the master component, go here and find out the flow rate. Master component flow rate, which one you are looking for? You're looking for methane, you're looking for oxygen, okay, and you're looking for carbon dioxide, okay. This is what you're looking for, molar flow rate, and also you're looking for nitrogen. I think you're looking for everything, right? Just carbon monoxide and what else is left? Hydrogen. Okay, or add all of them. You can add all of them if you have a new version. Similarly, you can do the same thing with the liquid stream. Show table. Okay, open this one. Remove the variables that is not required. Now add the variables which are required, which is master component, molar flow. So I need all of them. So I click one, press shift and last one, and then click add. Okay, done, and close this one. Now if you zoom out, you can see clearly that in case of here I didn't change the units, that's why it is in pound mole per hour. Doesn't matter, that is pound mole per. What is important that since we only have the gas phase reactions, we will not get any liquid in the reactor. Okay, that is why it is 0, 0, 0, 0. Since we have only a gas phase reaction and we are expecting only gases to be formed, okay, hydrogen to be formed in the terms of gas. So you can see here the amount of hydrogen that we are producing is 328.9263 pound mole per hour. You can convert this one into kg mole per hour also. Similarly, we have producing carbon monoxide. We also have nitrogen. Nitrogen we are not caring about because nitrogen is an inert gas. It does not involve in the reaction. So whatever the amount of nitrogen that is entering, the same will be leaving out. Okay. Similarly, we are also producing carbon dioxide, oxygen, and methane. So we are converting methane. What you can see here, methane in this selection is only happening to be converted 50-45%. Okay, if you have 100 kg mole of methane entering, only 45 kg mole is converted. 55 pound mole is not converted. Okay, again in the later exercise I will do how we can improve the conversion of methane by using a recycle. Okay, but here you can see that still we are able to produce carbon dioxide and carbon monoxide, which in the next class, on the next lecture, we will try to minimize it, or indirectly we will try to increase the production of hydrogen. Okay, so this is all about in today's lecture. If you have any questions, please don't hesitate to ask now, or if you have a question, ask me now, or if you want to ask me later, no problem. Again, yes, yes,
Doctor, for the conversion reactor, if you
yes.
double click on it to go inside.
Okay, this is the rector.
Okay. So it says like it's only using reaction one.
Yeah, okay, what is happening? Let me tell you. If you go back to your previous case in properties, where you add your components and set, if you look at here, set number one. In set number one, this is your group. Okay, as I told you before, in the group you'll add all the directions. So by default, the name is set dash one. Inside set dash one, you have both directions. Okay,
Uh,
so this is the name of the set or the group that is added inside the rector, and inside that
I
set you
understand.
have corrections. Okay, understand? So you need to create a group. In the group you need to add the directions if it is similar type. For example, if you have the third reaction which is not a conversion reaction, that is a kinetic reaction. So for kinetic reaction you need to create another set. Okay, so in that every set have a certain group of reactions. This set have only conversion reactions. So you can rename this one also. If you want to rename, you can rename this one. If you want to get a clear idea like what kind of, if you have many reactions inside your system, you can create one separate group and rename those groups according to your needs. But in this one, I keep it as default. So set dash one is basically a group that contains both directions. Okay.
I
Okay.
get that, doctor, but when you
Yeah.
go inside, you see
Yes.
if you go to the reaction bar at the top,
Yes.
okay,
Yeah.
go to
Here,
the
if you
right
click
side.
here, they will only create a group.
Yeah, but to the right of that, you see where it says
Yeah.
RxN1.
Yeah. Here, if you click here, you can have both directions.
So if you
Okay.
change it to reaction two,
Doesn't matter.
wouldn't that
Doesn't
change?
matter. It's just for information purpose. They will show here only for information purpose. Okay. If you want to see what is reaction number two, you can see here. If you want to see reaction number one, you can see here. But this rector is using both directions. Okay, because they are using the reaction set, it means they are using both directions. This is only for display purpose. If you want to
Oh,
see different reactions that inside the set one, you can go one and you can see two. Even if you want to open that reaction, you can click and open it also. Okay, if you do by mistake, if you do some mistake, you can open it from here instead of going back. You can open the reaction number one from here and you can play with this one. Okay, this numbers, and see if it is balanced or not balanced, or you can change the conversion also. Understand? So it is only for your help, like you want to open, you want to change something, or you want to display some results. That is how you can understand.
okay, thank you.
Okay, any more questions? Ask, huh? This is
So,
important. Yes.
when I change the mass flow rate from kilogram per hour to pound per hour, from it change in the unit set, but it's not change in the simulation.
Yeah, for here I think you mean to say.
Yes, it's not
Yeah,
change
here
there.
this one, here
I
you need to go not total, you need to go to component flow rate. Let me go down. I think this one is called which one is the name? The name which you want to change here is penetration mass. Let me see one by one. Yeah, this one. You can see here, this unit you need to change. Component mole flow. If you change this one into kg mole per hour, then it will change in the table.
okay,
See, it is changed. Okay.
okay,
Now it is in kg mole per hour. So the first one, the component mole flow, because this is not the total flow rate. This is the component molar flow. That's why you need to go and change the unit set of component molar flow. Okay. If you want
Okay,
to change
thank you.
the total flow rate, then obviously you need to go to total mole. Any more questions? No? I will share this chapter, and also I will share today video also, okay? So please go through with the lecture notes and video and practice. And again, I just want to remind before you leave, next week, which is on 27th of October, you have mid-exam 1 or in-semester exam 1, okay? That includes everything up till today. Obviously, you have another class which is on next week Sunday, okay? That is not included. Whatever we study on Sunday, that is not included in the exam. Whatever we study up to today, that is included along with the theory. Okay?
Okay, doctor, for when we do the simulation, do you need like a video or can we just take screenshots? Because it always takes forever to upload the video.
Yeah. For in case of exams, what you need to do, you keep your, just like your quizzes, right? Your camera's supposed to be on, okay? And when you do the simulations, you will send me what you call your simulations, okay? Very important, your simulations. And if I ask you any theory, then you need to type your theory or write your theory, and then you can send the theory part and also your simulations. Okay, obviously in the questions, I ask you to write down the answer on the paper. Okay, that you need to scan along with your simulation and then send. No video, no need for video. Okay. All right. Okay, everyone.
Okay, Doctor, but have we write it by our hand? It
You
take
can write
time
with
to
your
check.
hand. Okay, if you want to type, also because this is the good thing about using this online session. You can even type also. Okay, if you want to type it, type and then send. No problem. I don't mind. But you need to send both things. Okay.
Okay.
I think it is better for you to type, because if you write down, then you need to scan and then you need to send. It will take time, right? But if you type by hand, then it is easy. You can type and you can send the file to me. So when you're typing, make sure you type everything, and then you save that into a PDF form. Okay. For example, this is my Word file. If you're typing everything here, you need to go to File and save it as, like here, save it as PDF. Okay, you have the option here. If you go down, you have the option to save it as PDF. Save your file in PDF form and then upload. Okay, when you upload that one, they have less chance to become corrupted, and I can see those files easily. All right.
Okay,
I
Doctor.
hope everything is fine with you. Okay. Even if you have questions later on, you can ask me. If you don't have any questions, then you will leave one by one. Then I will leave at that.
All right, have a good day.
Okay, take care. See you. Bye.
Thank you.